Okay, we're ready for the last video of Chapter 5, Section 7, Part 2. We're going to be talking about changing bases, still using the change in base formula, and solving application exponential equations, and some more difficult exponential equations. So here we go. A $5,000 savings bond will double in 4 years. Give a formula for A of t. Now, usually when we're talking about money, we use the 1 plus r over n to the nt power formula. But in this case, we're going to use A of t equals a naught times b to the t over k formula. Okay? Label all the variables for me, would you? What's our initial amount? How much do we start with? We start with $5,000. What's happening to the 5,000? What's B? What's happening to it? Oh, it's doubling. That means B is 2. It's growing. How long does it take to happen? How long does it take that to happen? Oh, it takes 4 years. Oh, we have enough to write our formula. We start with our initial amount, which is $5,000. We're doubling it every 4 years. And this will work for any time period t. And there you go, that's the formula. How long does it take to triple? Well, if you started with 5,000, how much do you end up with if it triples? Well, that's 15,000 times 3. So it equals 5,000 times 2 to the t over 4 power. And you just need to solve this for t. And we've done this a couple times before. I would divide both sides by 500, so it's equal to 3 to the t over 4 power. Now the t is not where I want it to be, it's in the exponent. So I'm going to take a log of both sides and make this little baby a big baby. So I have the log of 3 equals t over 4 times the log of 2. And now just solve for t. T would be equal to the log of 3 divided by the log of 2, but the whole thing would be multiplied by 4. So in your calculator, type log 3 divided by log 2, and then multiply, then hit enter, and then multiply that answer times 4. Answer? About 6.34 years. That's how long it would take the original amount to triple into $15,000. Okay, so this isn't an application problem, but I still want us to solve it. These start to get a little bit trickier. So how would you solve this one for x? Well, x is in the exponent, so we're going to end up having to take a log or a natural log on both sides. Now, here we have power to a power. That means this really says e to the 3x power equals 200. Is there any way to get that 3x power out of the exponent? Well, certainly. You can take it, throw it out front, make it a big baby. Now you're going to take the log of e, or you're going to take the natural log of e. Well, you're going to take the natural log of e. Oh, and look who just showed up to the party. It's Lenny. Say, get out of here, Lenny. Oh, you know what I forgot? I forgot. If you take the natural log of one side, you got to take the natural log of the other side. Regardless, now I have 3x equals the natural log of 200, because Lenny was just equal to 1. And just divide both sides by 3, so the natural log of 200 divided by 3, and type that into your calculator. See what you get. It's about 1.7661. Now, there are other ways to do that problem. You could have taken this 3 and thrown it out front and just taken the natural log of e to the x equal to the natural log of 200. Now, how did that help you? Well, if you divide both sides by 3, you have the natural log of 200 divided by 3, and here you have Lenny again. Well, Lenny is really just the log in base e of e to the x. See you later. X equals the natural log of 200 divided by 3. So this was just an alternative way to do the same problem. Doesn't matter which way. I really like this next problem. Remember the rule of 72? It had to do with doubling. You need to show me that the rule of 72 is actually more accurate when you make it the rule of 69.3. Show that 69.3 divided by r percent is more accurate than 72 divided by r percent when r is compounded continuously. Remember, rule of 72 had to do with doubling. Doubling. How long it takes something to double. You just, if it's compounded at 8%, do 72. So if r is 8%, this is a side example here. You do 72 divided by 8, and you say, oh, 9 years or days or whatever's happening. Okay, so here we go. This is a cool problem. Well, since we're compounding continuously, we have a compounded continuously formula. It's the new amount equals the original amount times e to the RT. Times e to the RT. Okay. Now, a tricky part about this problem is, remember, we're trying to show that this is more accurate. 69.3 divided by r. So we actually don't know what r is. We don't care what r is. It could work for any r. But here's the deal. Remember how r here is as a percent? But when you plug it into the formula, r must be as a decimal. Well, whatever r percent was as a decimal, it's 0.01 r. Think about that. That's because you're multiplying. When you go from a percent to a decimal, you're actually multiplying by 0.01 or dividing by 100. And that's why you get 0.01 r. So for instance, if you had like 36%, divide that by 100 and you get 0.36. Or you could say 0.01 times 36. So here's your 0.01 r. Do you see it? All you're doing is moving the decimal 2 places. Okay, now, do we know the initial amount? No, but again, we don't care. We just pick some arbitrary amount. Make it $1 for all we care. And we want to know how long it takes to double. So what would the new amount be? Well, it would be 2. Okay, so e to the r is 0.01 r. We don't care what r is. But instead of r, I'm going to put 0.1 r. And t, we don't really care about either. We're trying to figure out what t is. So let's see if we can solve this. Solve this for t in terms of r. Well, this really says 2 equals e to the 0.01 rt power. Again, we want to get t by itself, but it's in the exponent, so I need to make it a big baby. So this whole thing is now out front. But am I going to take the log or the natural log? Well, since there's an e, we need to do a natural log. Oh, and look who just showed up. There he is again. Lenny, get out of here. Lenny's always trying to show up to the party. Okay, now we can get t by itself. All we do is divide the log of 2 divided by 0.01 r. Well, remember, we're trying to show that this is more accurate. That's a more accurate amount. Well, in your calculators, I want you to type natural log of 2. Why did I put log there? That should not be log. That should be the natural log. Come on, Mr. Williams, get your head in the game. The natural log of 2 divided by 0.01. Type that into your calculator. And you will get, look at that. You'll get t is about 69.3 divided by r. We didn't get rid of the r. We just took, natural log of 2 divided by 0.01. And looky there. That means the time it took to double is better approximated by 69.3 divided by r. Maybe we should call it the rule of 69.3 and not the rule of 72. Alright, now I want to give you some difficult exponential equations to solve before we're out of here. Okay. Now I want you to solve for x. The problem is you have e to the 2x and e to the x. Oh my goodness. All right, well, how are we going to solve this one? Well, I want you to think about the fact that you can rewrite the first guy as e to the x with a 2 on the outside. You agree with that? That e to the 2x is the same thing as e to the x squared, because a power to a power means you multiply. And now you're going to do something called substitution. You're going to let, just pick some variable. I'll choose y. Let y equal e to the x. Check this out. That means you can pick up this y, and wherever you see the e to the x, you can put it in. So actually, this equation says y squared minus y minus 6. Well, now we can solve this rather easily by factoring. So y could be positive 3 or y could be negative 2. But here's the problem. We're not trying to figure out what y is. We're trying to figure out what x is. But wait a minute. We said y was really equal to e to the x. So put both of these values in for y. So 3 could be e to the x, or negative 2 could be e to the x. Now let's solve both of these. How do we solve these? Well, take the natural log of both sides, throw the x out front, natural log of both sides, throw the x out front. Lenny has showed up to the party. Get out of here, Lenny. Get out of here, Lenny. I'm left with x is the natural log of 3, and x is the natural log of negative 2. Now, one of those doesn't make sense. One of them is stupid. You cannot take the natural log of a negative. That would imply that e to some power is a negative number. That's stupid. There's no solution. He's extraneous. But here, the natural log of 3, type it into your calculator, about 1.0986. Give or take. I rounded to 4 decimals. 3 decimals would probably be okay. Okay, let's try another one where you have to do that substitution thing. Alright, what we're going to do here is the split approach. We need something simple to let y equal. Let y be, and it's probably going to be this middle guy here. It usually is. I'm going to say 3 to the x. The problem is here I don't have a 3 to the x. I have a 3 to the 2x plus 1. So let's use the split approach. Let's make this say 3 to the 2x power times 3 to the first power minus 7 times 3 to the x plus 2. Now I almost see a 3 to the x over here. I see 3 to the 2x. This is what I'm going to do. Take this 3, put it out front. But this 3 right here, make it 3 to the x squared. Do you buy that? 3 to the x squared? Power to a power means you multiply the powers. Alright, now we're in business. Minus 7 times 3 to the x. Now I can do this substitution thing. So instead, everywhere I see a 3 to the x, I put a y. So I have 3y. Pick him up. Put him right here, 3y squared minus, put him right here too, 7y plus 2 equals 0. Hopefully this bad boy factors, and he certainly does. He factors to 3y minus 1 and y plus 2. That is not correct, Mr. Williams. You just messed up. It'd be y minus 2. So y could be 1/3 or y could be 2. The question is, are you done? Yes or no? You're not done. Remember, we said y was really 3 to the x. So, over here, I'm going to erase some of this arrow to give myself some space. Over here, instead of y, we're going to put 3 to the x equals 1/3, and 3 to the x equals 2. Because we're just replacing these y's down here, guys. Well, if 3 to the x is 1/3, that one's pretty easy. What's x have to be? Well, 3 to the negative first power equals 1/3, so x is just negative 1. Now, if you didn't like that, you could have used the change of base formula. You could have used, you could have done a log of both sides. Now on this one, I would say do a log of both sides. Throw the x out front, so it'd be x log 3 equals log 2. Notice I did a regular log and not a natural log. So x is equal to log of 2 divided by log of 3. Type it into your calculator. You'll get about 0.6309. Your book will actually do this. I don't know why they do this. Instead of approximating the answer, they leave it as a single logarithm. They say, oh, well, that's just the log. Remember, the top number is always the big number, and the bottom number is always the base. They'll say that's just the log in base 3 of 2. I would accept the decimal approximation. The book wants the exact number. Whatever. I would accept either one. You get the point. Okay, folks, that's all I got for Section 7. Hope you enjoyed Chapter 5. I know I did. I'll catch y'all later. I'm out.